Okay, so we're going to be talking about numbers today and what we learn in school, and also about the history of understanding of number. Over many centuries, ideas and knowledge of numbers was spread along trade routes with invading armies. And what you see in the map there, the one on the upper one, is the trading routes by sea and the Silk Road in red there between East and West. And below you see North Africa, and you see how the Islamic culture spread across North Africa and into Europe. We'll say more about that later.
With at GTEN, we use the spiral learning path. So the idea is that starting from when you're born, really, you become aware of the world around you and you work along the spiral path. But each year of your life or throughout your life, you keep repeating, coming back to the same information. Only as you develop, you hit it at a different level, you learn it at a different levels. We're starting at the bottom, so we're going to cover all different levels of learning. From counting numbers, this is all about numbers, so counting numbers, then we're going to add zero, then we're going to add negatives, fractions, we've got the integers, all the integers, and we're covering the different types of numbers. You've got the irrational numbers, the rational numbers, the real and virtual numbers, and we're looking at all the number systems, and you can see in the Venn diagram.
Yeah, so looking at this, we want to look at numbers in the last 5,000 years and the numbers in our lives. And the dates you can see, there are a lot of things on this slide alone. So the date on the timeline gives the start of period of development and of sharing of new numbers, as in new number knowledge between different parts of the world. So we can see the Pythagoras theorem on one side, and going through, you can see the pyramid, you can see so many things, Einstein, yeah, like that from start to finishing, and which is sharing numbers knowledge. And we can see Greece, 800 DCE, and there are so many things. We'll just find a way to just give us here and there today. And you know that in the last 5,000 years, definitely all of us, we've come across number in different ways. Tony, you can probably add on it.
Well, yes, I've so many ideas. I've just focused mainly on numbers, and mainly actually on the Pythagorean theorem here, which of course wasn't invented or discovered by Pythagoras. It was known thousands of years before by the Babylonians, and the Greeks probably heard it from them, and the Chinese. What we've got up on the right is Einstein and Andrew Wiles, and there's something that looks a bit like the Pythagoras theorem. A to the n plus b to the n is not equal to c to the n. It is for n equals 2, but otherwise it's not. And these sort of awareness of number has developed over thousands of years.
To review all the number work done in school, from our early years in school. So we are going to be looking at it. Now, we want to see ourselves as one of our students, how they came about, how the first time you heard about numbers, what is it, how was it for you? So today, to review all the number work done in school from early years to school living, you will learn that school number work is actually about groups or fields of numbers. And we want to understand maybe transformation in space. It can help us to understand that. And 4-dimensional numbers with 3 spiral dimensions, and the time as the 4th dimension. So this number system can help us to understand higher mathematics and even science. Let's say, for example, general theory of relativity. So there are a lot of things we'll be able to discover that this little number 1, 2, 3 that we started with, they contribute to bigger theories that is being used in developing technology, even science that is being used in science.
We're going to be telling some jokes. Now, these are actually mathematical jokes, and we want you to think how you can use these in your class. So why don't you do calculations in a game reserve? I don't know, Caroline. Why don't you do calculations in a game reserve? And here's the maths. Because if you add 4 plus 4, you get 8. We're talking about different numbers, as Tej just said, and we specifically put in the Year 9 curriculum of South Africa, the CAPS in this one, but the terms used here, we're going to be talking about rational numbers, irrational numbers, commutative, associative, distributive, additive, and multiplicative inverses. What we'd like you to comment in the chat is what these numbers mean. What do the highlighted words mean? So if you could just comment in the chat any of those that you can think of.
But again, it's language, isn't it? These are quite difficult words. They're not difficult ideas, but they're quite difficult words to learn.
So looking at this one going on, so we also pick from year 10 and 11. So basically, we want to focus on complex numbers. And we will be able to see from this that it is possible to square certain complex numbers and obtain negative real numbers as answers. And we want to say, okay, what are complex numbers? Probably we don't actually understand it yet, but that we are going to be able to see as we proceed. And we also want to understand that real numbers can be irrational or rational. And we need to actually take note of this. So nature of rules, so solve quadratic equation, which is very important. Like, let's take for this example that is on the board, that is projected here. Now, show that the roots of x squared minus 2x minus 7 equals to 0 are irrational. So we'll be able to see that as we go along. So you are going to do some university level mathematics today. They are not fair. We don't need to be afraid of it or be scared that, oh, no. Now, just like we said, you need to put yourself in the position of your learners. So we want to look at some of the university mathematics that we have done, including algebra with complex numbers. You will learn about 2-dimensional and also 4-dimensional numbers and their uses in science.
Let's go right back, and we want you to think of yourselves as learners now. What experience do the learners have? So when you were very small, you learned to count, maybe before you went to school, and you've learned more about numbers each year in school. And as a learner, you now know about counting numbers, negative numbers, fractions, and irrational numbers like √2 and pi. And you know something about the rules for addition, subtraction, multiplication, and division for combining numbers. Now, today, we're going to start right at the beginning of this story, and we'll see how people met numbers when they couldn't solve certain problems. They had to discover new types of numbers. As we mentioned before, you sort of come back to number knowledge you had before, and you build on that. Now, the little diagram at the bottom there, little picture of the ducks, we have an expression in English, let's get our ducks in a row. And all it means is let's get things sorted out so we really understand them. And one of my friends, Mike, did the illustrations of ducks. Now, we'll meet higher dimensional numbers and their uses in science. And we'll meet school mathematics as a set of rules that must be followed exactly like the rules of a game. You really have to keep the rules. And these rules give us what mathematicians call a group. We'll understand that by the end of this session. And apart from numbers, the group rules, just the rules that we meet in school mathematics, they apply to many other systems that are essential to higher mathematics, physics, and chemistry, not just arithmetic, not just calculations with numbers.
Right, time to wake you all up. What did 0 say to 8? Have the picture, Tony. Does the picture not come up yet? Oh, go for the picture, Tony. Nice belt. What are numbers? Now, depending how old you are, depending where you are on the spiral, you're going to answer this differently. But we want to think about what you think back to when you were very young, or you've got very young learners in your life or in school. First, you learn to count up to 5, 10, 20, 100. Do you remember when you realized that counting goes on forever with no end? It's really a very defining moment when a child starts imagining infinity.
And very young children are often very proud that they can count to 100. And then a little bit later, they realize that, well, this is great. I could go on and on forever, but I don't want to waste my time doing it.
Okay. So the rules of arithmetic that you have learned. So we want to look at this rule. So let's look at what we have here. We have 5 plus box equals 8. So what will you put inside the box? That's very easy. Definitely we know that we will put 3 in the box. Easy. We learned that in year 1 already. So early in your lives, we met adding and sharing. So where you see that learners, you are asked them to, okay, yes, you want to share a certain, maybe sweets, 5 sweets among five students. And then they will be able to tell you how that should be shared. And adding and sharing take us beyond simple counting into number work. So it goes beyond that. It takes us into, like, we're already doing arithmetics. At that stage, you understood numbers are not just for counting. So when we get to when you start counting 1, 2, 3, at that level you might think it's just about counting. But when we get to a level of adding or sharing, then you know that it goes beyond just counting. Numbers are objects. We combine according to agreed rules, which we call arithmetics. You can have 3 plus 5 giving us 8. So the more we know about arithmetics, the more we see that it is a useful tool for solving all sorts of human problems.
Okay, so we're going to talk about inverse operations now and zero. We're extending our ideas from just 1 to 3 and so on. So addition, it corresponds to increasing the size of a collection of objects by combining 2 sets. And so here you see 5 combined with 3, 5 plus 3 is 8. We undo addition. What happens? How do we undo that process that we've just seen? Yes, what we do, and if you look at what's happening in the box, we undo it by taking away 3. So subtraction reduces the size by removing some of the objects. It undoes addition. So this is what we mean by inverse. One process, that's addition, acts, and then the other undoes that action. Addition and subtraction are inverse operations. What about if you take 5 from 5? What would the answer be? Of course, 0 goes in the box. And it would be the same, whatever number you took. If you took it from itself, you'd always get 0. Lots of people have put that on the chat. Well done. So if we use numbers to describe the size of a collection of objects, we need a number for a set that's nothing in it. So small children know about the counting numbers starting with 1, and then they have to learn about the number 0. And it was the same with mankind. For thousands of years, people didn't think of 0 as a number. Now, of course, they knew that there was sometimes nothing there, but they didn't describe a number to characterize that. And it's only as recently as 500 years ago, scholars in Europe were still asking, is 0 a number or not? The debate about it.
So did you hear about the mathematician who was afraid of negative numbers? Whatever was that? It was because he'd stop at nothing to avoid them. Sorry, that actually, I find that very amusing. So every time it gets me. I love this image. This is a very beautiful image and very helpful when you're talking about negative numbers and manipulating.
Well, we've just talked about 0, haven't we? But now we've got to go, we're going to go beyond 0. We're going to go down into negative numbers. And a good while earlier, somebody mentioned negative infinity. Well, we hadn't got even into negative numbers, but now that's where we're going.
So again, we want you to think about back when you were young and you didn't know about negative numbers. So put your hat on of before you learned about negative numbers. What would you put in each of these boxes? Put them in the comments, or at least some of them in the comments if you can, but go through them. There's 6 to do. Go through them and think about what you'd put in each of those boxes if you didn't know about negatives.
Put the answer on the chat if you like.
I'm assuming everyone's had a look down them, and I don't know about you, but what occurs to me is that the ones that are difficult, as in 3 minus 8, 5 minus 12, these are the ones that show you, that highlight the misconceptions that primary school children experience, that they might answer one as 5, but answer them in the positive, 8 minus 3 or 12 minus 5. So those they help you to contemplate on misconceptions. Thank you, Tony.
Okay. Following up on what Caroline just explained now, so we want to look at closure. And I just want to look at the comments from Talu. So when we look at 8 plus 3, 8 plus 3 equals, definitely we're able to find answer to some of this from the previous slide. Talu said, I used to say impossible. So that is the truth. That is what you get from the box that is painted in blue. Is it blue or green? Which of the two? So that box, you think, learners will tell you, or when you don't know anything about negative numbers, then they will tell you it is not possible. So Melin also said, many children subtract the smaller from the larger number, regardless of what the problem requires. So they just overlook and say, no, it is just whatever it is, this can be done. Yes, when you only knew about the odd numbers, 0, 1, 2, 3, 4, and not about negative number. So what will you put in these boxes? Then, and that we've already addressed. So we already know 8 plus 3 gives 11, 5 plus 7 give us 12. And then when you add 2 whole numbers, you get a whole number. When you add 2 whole numbers, you get a whole number, and that is 8 plus 3, which gives 11. So addition is closed for the set of whole numbers. Addition is closed for the set of whole numbers. But let's look at this. When you subtract one whole number from another, you don't always get a whole number. What are we saying? So when we have 8 minus 3, which gives 5, but if you do the opposite, like 3 minus 8, that doesn't give a whole number. So subtraction is not closed for the set of whole numbers. Okay, and moving forward.
You need negative numbers, don't you, if you're going to put something in those boxes. And so what we need is we're going to introduce a new set of numbers, which we had in the joke, and that is the negative numbers as well as the positive. So what we knew about was the natural numbers in a sort of gold, yellow gold color inside there, and the whole numbers in blue, as you see in the diagram up on the left here. But this diagram shows you the natural numbers and 0 all going together. And then now we're going to extend our ideas to integers.
We've had some very, I think, useful comments here. And this is not just for primary school teachers, this is secondary as well, because some secondary learners still have misconceptions that they got all the way through their primary school years. So we've got many children subtract the smaller number from the bigger, regardless of what the problem requires. That's Marilyn, and that's what her experience in class. That's what's happening. That's what I was thinking they might do. Nettie, and I seem to remember this from my years as well, this rings a bell with me. We were taught you can't subtract bigger numbers from smaller numbers. I remember that being said to me. And then Simbiwe says some children say that we're not allowed to subtract a big number from a small number. These are very useful reflections, and we need to be very careful, A, what we say to the learners, and B, to be aware of what is going on in their heads.
Well, that's absolutely right. And the problem is that the teachers put these strange ideas into their heads. The only reason they can't subtract bigger numbers from smaller numbers is because they don't know about negative numbers. And the teacher could at least say, well, we'll learn how to do that next year, rather than implying it can never be done. Because indeed it can, as we know. So now, if you want to, why don't you get a little bit of exercise and stand up. Now sit down. Now stand up. Now sit down. What do you notice about these actions? Put some comments on the chat about that. What happened? What do you notice about those actions? We're going to do some similar things, but we're going to think about it this time. Put your coat on. Imagine putting your coat on and you take it off, then you put it on again and you take it off again. So what can you say about these actions? What do you notice about them? And would tying and untying shoelaces do an undoer process? What we're getting at here is that all of these actions, yes, we've now got some answers saying that the opposite of each other, one action undoes the other. Undoes it.
Undoes
it. Yes, yes. So just as we saw that addition and subtraction undo each other, reverse the process if you like. They're inverse operations, that's what we call them. And that happens with multiplication and division too. Very importantly, in class, then get some of your learners to explain their choice of yes or no, because, you know, that's what you want to do. Have a discussion about why they said this or why they said that. And that will help the other learners to get the right answer.
Okay, thank you, Tony. That was very valuable. So why won't Mzu drink a glass of water with 8 pieces of ice in it? You might want to pause a moment to actually let them think about that one, because I did work that one out. Because it's 2 cubed. I love that one. And I did work it out. I said it was something to do with being cubed, but I didn't.
But also, when it comes to language, you could talk about the spellings there, TWO or TOO, couldn't you?
Absolutely. So you got the language, the spellings, and the meaning of everything. It's very nice. So what are inverse operations? I want you to close your eyes. Everybody, I'm not joking. Please close your eyes, because if you see this, it's just visualize it. So you're going to see your numbers in your mind. Choose a number and remember it. Now make a mental picture of your number, whatever form that takes for you. Now add 4 to your number and think now of the new number. take the new number and subtract 4. Now think about what you've just done. What happened? Reflect on it for a moment. Now open your eyes and write down your final answer. Now we want you to explain it. Put it in the chat. What happened? How will your learners of any age explain what just happened? Now, I know that some of you are typing. It just takes time for the typing to come through to us. So I'm going to assume that some of the answers are going to come in. But what we're looking at is literally addition and subtraction undoing each other, like the shoes. And this is an inverse operation. Suppose you chose 11 to start with. 11 plus 4 is 15. 15 minus 4 is 11. And we're showing using the shoes as an example.
So negative numbers and inverse pair. So looking at this, what is the answer to 9 minus 13? Now that we've been able to meet negative numbers. So looking at this, 9 minus 13, what are we getting from this? When you did not know about negative numbers, you thought there was no answer. So you would think this is not possible. Just like we've already mentioned, and it has been added on the chart, that this is impossible. We are not allowed to. So you need negative 4 to be able to do this. Now, to be able, and let's look at it. What number do we add to 13 to make 9? What number will you add to 13 to make 9? So you will need negative 4 for it to be 9. So subtraction is just addition of the inverse. If we have 4, the inverse will be negative 4. And let's look at this one. 13 plus negative 4 equals 13 minus 4 equals 9. So let's, now looking at this number line, so we start from 13 on the right side, and then you add 4, negative 4, which is the inverse, the negative 4 to it, and then you're counting backward. That gives you 9. So that is 13 plus negative 4, which is 9. And now, so 9 minus 13, we look at from 9 on the number line, minus 13, you count backward. So we count 8, 7, 6, 5, 4. Then you get to negative 4. And that is basically what we've just explained. Subtraction is just addition of the inverse. So the number minus 4, which is written as minus 4, is called the inverse of 4. Because when you have 4 plus the inverse of 4, you get a 0.
Now, what we've got to bear in mind is that subtraction means adding the inverse here. So we have these rules that are at the top of the board, and a lot of children are taught that two minuses make a plus, and a plus and a minus make a minus. But why does that happen? Now, if we think a bit more about the number line that Tejamade was just talking about, I think we can make perfect sense. So if, for example, we've got 7 take away minus 4, what we do is we add, taking away is adding the inverse. So we add the inverse of minus 4, which is plus 4. Easy, 2 minuses make a plus if you want to say, but that's why it happens. And it's really important that the children understand why. They don't just learn a rule that makes no sense. So if, right, so subtraction is just the inverse, additive inverse, okay? The addition of an inverse, I mean. Subtraction is just the addition of an inverse. And so taking away -4 is the same as adding +4. We've just seen that. And notice that the arrows that we've been putting here go in opposite directions. And in fact, the right name for them is vectors or directed numbers. But it's not important necessarily, unless it is in your syllabus in your country. They don't need to know that term, directed numbers or vectors, in South Africa, but it certainly would if you were in England. There's a lot of work done on it here in our syllabus. So, okay, so here, if we have 7 and we add -4, oh, sorry, if we subtract -4, we add +4, and you see the arrow there goes from 7 to 11, +7 to +11. So, okay, I hope this is making sense. The number -4 is called the inverse of +4 because when you combine them, you get 0. And it works with all numbers. Every integer has an inverse such that the number added to its inverse gives 0. And what we've got is a number system, and we're using just the rules of school arithmetic.
In primary school, we learn we can put numbers in boxes. We answer questions, we put numbers in boxes to make I call them number sentences. You can speak out loud what you're doing. But it's the same as solving equations. It's the same as algebra in secondary school. So we know to solve equations in the form a plus x equals b. So we know how to do it when b is greater than a. Using this terminology is often different to the way it's taught in school at the moment. So really think about this. If you're not already doing this, think about this to help the learners understand this. Add the inverse, which is -a, to both sides to get x equals b minus a. So instead of taking a away from both sides, think about saying add the inverse, not take away, but add the inverse, which is -a, to both sides, which gives you the same result. But you've got the additional element of understanding when you're talking about adding an inverse rather than taking away that number.
It's why
Now,
you add the inverse, isn't it?
Yes, it's why you add the inverse. It's why you're taking away the a from both sides, is because you need to add the inverse to get 0. So when we didn't know about negative numbers, could we solve 9 plus x equals 5? No, because 9 is greater than 5. And it has no solution in the whole set of numbers, but it has a solution if you know about negatives. So it has a solution in the set of integers. So your whole numbers are 1 to infinity, and we can include 0 in our natural numbers. And then outside of that, we have a set of integers. So you've now got 0, your natural numbers, which is 1 to infinity, and negative numbers, -1 to -infinity. So for all equations like this, you have solutions. To have solutions, you need to work with the complete set of integers.
And it was like this historically. When you couldn't, in the past, when people couldn't solve equations, when they couldn't do some calculation they wanted to do, they had to realize that they needed a different sort of number and add to their ideas and expand their knowledge and add to their ideas about numbers. Now, the same properties, again, as Caroline's just been talking about, apply to fractions or rational numbers. Fractions are called rational numbers by mathematicians, but we call them fractions in school most of the time. Now, there was a time when you and children first learn about negative numbers, and another time you met fractions. When you didn't know about rational numbers, fractions, could you put in answers in these boxes? When you didn't know about fractions, could you fill those boxes? Well, again, we've given you a clue because one of the boxes is not empty, it's colored. And so what happens? And without fractions, could you solve these equations? So these two ways of doing it, you could say on the left is the primary school way, and on the second is the secondary school way. And mathematicians call fractions rational numbers. For example, 10/3, which is 3 1/3. So you need to have your knowledge of fractions to solve these equations. So if we're just in, when you add, subtract, multiply, and division and divide rational numbers, except 0, you always get another rational number. It's a closed system. If we were just talking about whole numbers, it isn't closed, as we saw for subtraction and division. So now we put another layer of numbers outside, but also including everything in between it, inside in this diagram. So natural numbers, integers, are rational, but in that outer green area, those are the rational numbers that are not whole numbers, not integers.
All right, so we have been putting numbers in boxes and also solving equations for addition. So now it is time for us to think of multiplication. So if we have a, b, and x as integer, just like Tony mentioned, now we have moved from natural numbers and 0. So we added another layer, which is integer. Now we've gotten to the level of rational numbers. Now, so we have a, b, and x as are integers. A and b are known, so you know the number, and you have to find x. Can we solve all equations of this form? When you have ax equals to b, are we able to find it? And I want you to use your thumbs down or thumbs up. Now, for example, when you have 11x equals 120 for integers, are you able to solve this for integers? Now, you use the inverse operation like on tiny laces. In this example, when you know about fractions, you can use the inverse operation and divide by 11 to find the answer. The answer is not an integer. When you have 120 divided by 11, so it is not going to give us an integer. Instead, it's a fraction, which is rational number, and it gives 10.90999, and it's reoccurring like that. So we need to extend our ideas of arithmetic to include fractions. So we need to extend it to include fractions, which is rational numbers, that it's now the next layer that we have added. Then all such questions have solutions. So when you see questions like this, 120 equals or divided by 11, then it has solution. And notice the answer is a rational number, which has an infinite decimal with a recurring pattern. Just like I mentioned, we can see that it is 10.909090, and that's how it continues. So it is it has recurring pattern.
Think about the camels. And another answer which was absolutely fine, 4.75 for the son would get 9.5, the daughter would get 4.75, and the servant would get 3.8. I think it might be a bit more than 19 there. And then it's Jacob says, maybe you couldn't have 9.5 camels, so you'd have to round each answer up, and he's got 9, 5, and 4, which makes your 19. So another answer. So there's different ways of doing it, but in some ways they're not terribly satisfactory. I mean, you could have camel for dinner, and I wonder if everybody's happy there. Well, you could look at this with, if the son got 9.5 then that's fine. It's exactly what his father promised. The daughter got 5.5, and that's more than 5.25. So she's done better. And the servant has got, he's got 4, and that's more than a fifth. So maybe they are all happy. But if they don't want to cut the camels up, what do? Is there a better solution? And what's wrong with this solution? So a wise man who was traveling on his camel came to their rescue, and he solved the problem like this. Along with the 19 camels, he also included his own camel to make 20. And then he gave the son half of them. He gave the son 10. He gave the daughter a quarter to make 5. And he gave the servant a fifth to make 4. And that's Jacob's answer when he rounded up. And that's fine. It's 10 plus 5 plus 4 is 19. And the wise man took his camel and rode away, which is quite a nice answer, except the fractions aren't exactly the same fractions of 19. They're actually fractions of 20. Okay, so let's move on now.
All right. So what is the additive identity? So what is the, yeah, I could see it coming there that was a wise man. Now, so what is the additive identity? Does every rational number have an additive inverse? Now, we've talked about inverse, where +4, -4. Now, does every rational number have an additive inverse? We talk of addition and subtraction are inverse operations, which we've been seeing all along. Now, complete this calculation when you have 5 plus -5 or -5, which is equals to 0, and is also the same for n plus minus n is 0 for all n. So this tells us that 0 is the identity for addition. 0 is
Tejmade, we've lost, I think you maybe have to unmute, Tejmade.
Yeah, thank you.
Okay.
All right. So I guess probably from numbers n and minus n are additive inverses. So subtraction is like adding an inverse, which is absolutely the same way everything we've been talking about. Yeah.
So what's the identity for multiplication? Teja's just talked about the identity for addition and subtraction. What about multiplication? Does every rational number have a multiplicative inverse? Now, do you know what we're doing now is we're doing for the rational numbers exactly what we did for the integers. So we're just extending the ideas a bit more. So now, just as 5 times 4 is 20, 20 divided by 4 is 20 divided by 4 gives us 5. 4 times 1 is 4. And it's true for all n that n times 1 is n. 4 times a quarter is 1. And it's true for all n that n times 1 over n will give you the identity 1. So we say that 1 is the identity for multiplication, and every rational number n, except 0, you can't divide by 0, every rational number except 0 has a multiplicative inverse, 1 over n and n. So here we've got associativity.
Sorry, Tony, I did have it. I just was muted. We've looked at addition and subtraction. We've looked at multiplication and division. We're going to look at associativity, which applies to, does it apply? What does it apply to? So we're going to use brackets in order to make the order of operations clear. So we can do thumbs up again, thumbs down. I'm going to call that the adding section, section A, the subtraction section B. Are the answers the same for section A, the adding section? Are the answers the same if you do those operations when you do the brackets first? Are they the same for subtraction? Thumbs up if they're the same, thumbs down if they are not the same. Again, it takes time for these thumbs up and thumbs down to come through. So if you can continue, Tony. So for addition, the answers are the same. Doesn't matter which order you do it in. So for addition is associative. On the other hand, for subtraction, the answers are different depending which order you do the subtraction in. So subtraction is not associative. Going on to multiplication, again, we're putting in the brackets to make clear which we're doing first. We're going to do section A is the multiplication, section B being the division. Are the answers the same depending which order you do it in, or irrespective of the order you're doing it in? Are the answers for division the same irrespective of which order you do them in? Nokana was talking subtraction, negative is thumbs down, addition thumbs up. It does take a long time. Marilyn says subtraction no. It takes a long time for the comments to come through, so please do make the comments, we will see them. Yeah, so yes, the answers are the same for multiplication, doesn't matter which order you do it in. And for division, they're not associative because the answers are different if you do them in different order.
So now we've met the word associativity. I mean, it's the experience of this happening is a common one that the children mention, not mention, but they happen to experience. But now we want to just see what this word is meaning. Now we've got commutativity.
Okay. So we have already seen associativity. Now we want to look at commutativity. Yeah. So what does it really actually mean? So when you have 5 plus 7 and you change the order to 7 plus 5, does it give the same thing? So 5 plus 7 and 7 plus 5 equals 12. But in the case of subtraction, 5 minus 7 and 7 minus 5, are they the same? Now, when we have 5 plus 7 and 7 plus 5 being the same thing, giving us 12, it shows that addition is commutativity. It's commutative. So why subtraction is not? Because 5 minus 7 gives you a minus 2, while 7 minus 5 gives you 2. Similarly, when we look at multiplication as well, 5 times 7 and 7 times 5. So we can see that addition is commutative, subtraction is not. And the same thing, when you have 5 divided by 7, is it the same as 7 divided by 5? It is not. So in this case, addition and multiplication are commutative, while subtraction and division are not.
So we're going to have a summary of rules now, and there's nothing new on this slide. It's all, well, there is a little bit at the bottom there, this word group, but actually This is what we've been talking about since the beginning of this session, the rules for addition of rational numbers. So we've got to remember subtracting is just adding an inverse. And these are the rules taught in school. All the number work done in school follows these rules. And rule number 1 has 4 parts to it, all about addition. The set of rational numbers is closed, it's associative. There's an additive identity, it happens to be 0, and every rational number has an additive inverse. So what we're doing here is just rules for calculating. It may look quite formal when it's put in all those words and it's all written like that, but it's what's taught in primary schools. Okay, the words themselves, the children meet later, and as you saw, they're supposed to learn them in year 9 in South Africa. Now, that was rule number 1.
Sorry. Okay, Tony, you go ahead.
That was rule number 1. Now, rule number 2 applies to multiplication, and we've got exactly the same pattern of 4 bullet points, 4 different sorts of properties for multiplication, same as we saw for addition. The set of rational numbers, leaving out the number 0, is closed under multiplication. For all rational numbers, A, B, and C, you've got associativity, that property. A times B first multiplied by C is the same if you multiply B by C first and then afterwards multiply by A. And we've got 1, which is the multiplicative identity, and the numbers come in pairs, which are multiplicative inverses of each other. In this case, addition and multiplication are commutative. A plus B equals B plus A, and AB is equal to B times A for all A and B. So just those rules that we've seen, leaving out the number 0, rational numbers leaving out the number 0 form another group, and we now have rules for addition and multiplication. Now, if we put everything together, that is, rule number 1 only applied to addition, rule number 2 only applies to multiplication, and when we go on to rule number 3, we've...
Yeah, so rule number 3 talks about the distributive law for combining addition and multiplication. Now, when we add and multiply rational numbers, we use the distributive law. So let's look at this. For example, 3 times, when you have 4 and 5 in the bracket, so that gives, you add 4 plus 5. Okay, what is it going to be? I think you can use the chart, and we can see the image here right beside it. 3 on one side, and the other side we have 4, which is 3 times 4, that gives 12, which is in the bracket, and 5 times 3 gives 15. And when you add the 2 together, you are able to get 27. So 3 times 4, that's the first one, and the other side, which is 3 times 5, which gives, everything gives 27. So rules for calculating, we've looked at rule 1, 2, and 3, which describe additive and multiplicative groups for rational numbers, and the distributive law, okay? The 2 groups together with the distributive law make up what mathematicians call a field. Now we are finding another word, which is a field. And from the chart, I could see somebody saying 3 times 9, which is 27, which is correct. So I guess this person went ahead to add 3 times 4, adding 4 and 5 together to give 9. And then you have 3 times 9, which is equals to 27.
So what we've had so far has only been about fractions, which we call rational numbers. And we saw that if you use your calculator and divide 4 by 33, just as an example, or any whole number by another number, what happens? 4 divided by 33. This goes on forever. It's a repeating decimal for 4 over 33 is 0.12121212. So this is how we write fractions as decimals, and they're equivalent to each other. So if you choose your own fraction and divide the numerator by the denominator, what do you get? Do you always find a pattern in the decimal digits? This is what you're looking for. You're looking for a pattern in the decimal digits. You see the pattern in 4 over 33. It's 1, 2, 1, 2, 1, 2. Yes or no? You can do the thumbs up or thumbs down if you like. Is there always a pattern if you divide one number by another? And of course, your number may actually terminate, but you can, like, for example, 3/4, it would end in 0, 0, 0, 0, and there's your pattern. But we don't usually write down any of those zeros. Ah, now I'm really interested. So sometimes there's no pattern. I'm really surprised. If you divide one number by another, do you always get a pattern? Now, it may be that your calculator rounds the numbers off but at the end. You've really, if you use a calculator, perhaps it will just chop off the rest of the repeating pattern. So you really have to do the division to make sure. But every time you divide one number by another, I assure you, and if you actually have a calculator that goes to more decimal places, you will see it happening, and you always get a repeating pattern. And it may be a repeating zeros that happen there. Try it for yourself. So this is the difference between fractions or rational numbers and irrational numbers. The thing is, you've been using irrational numbers, but they're not actually covered in everything we've said so far. We didn't say anything about irrational numbers, like the length of the diagonal of a square. So if the edges of the square are 1, then the diagonal is of length √2, and that is an irrational number. It cannot be written as a fraction. No way. Okay. And pi is an irrational number, and it can't be written as a fraction either. So you might say √2 was at 1.414, but that's an approximation. It's not the value of √2. And we could say that pi is approximately 3.142, but that's only an approximation. There's no pattern to the digits after the decimal point. You'll never get these numbers exactly, however hard you try. So what does your calculator give for √2? Is there a pattern there?
Sorry, Tony. Next, can you please ensure that you remain muted, because I've muted you like 2 times now, and it keeps coming up again.
Okay, so if you look at √2, it's 0.4142414141,35623, and it goes on and on without a pattern. Similarly, pi is 3.14159265535, and it goes on and on without a pattern. So that's the difference between fractions and irrational numbers. And when you put them all together, and you've got this outer dark green region in this diagram, you've got the real numbers, including some rational numbers, but including also irrational numbers, as we've just discussed. And we discussed the field of rational numbers and calculating the rules for calculating rational numbers. And actually, real numbers obey the same rules for addition and multiplication as the rationals. So there is a field of real numbers. So you're quite safe working with them, except that you can't get exact answers. So,
okay. So do we need to go beyond real numbers? From the previous slide, we could see that, yes, we've talked about rational number and irrational numbers. So do we need to go beyond real numbers? So the rational and irrational number together make up the real numbers. And each real number corresponds to exactly 1 point, on the number line. So it corresponds to a point on the line. And all the points on that line are represented by real numbers. So we call this line the real line. So this is called real line. You might want to look at the solution to x squared equals 2. What is x? What is the solution to x squared equals 2? So x equals plus root 2 or minus root 2. Our solutions to x squared equals 2. Do we really understand how this is? So what would be the solution to, if you have x squared equals minus 2? So we've done for x squared equals 2. What about x squared equals minus 2? If we only know about real numbers, we cannot solve the equation x squared equals a when a is negative. When a is negative, because squares of real numbers are always positive or 0. Squares of real numbers are always positive or 0. But that doesn't mean there's no solution to this question. So using the formula, which is x equals minus b plus or minus square root of b squared minus 4ac divided by 2a, for any quadratic equation ax squared plus bx plus c equals 0. We can solve this problem. We already know our a is 1, our b is 1 in this case. Okay, yeah, now let's look at this question, question 1, which is x squared minus 2x minus 7 equals 0. So for this first one, we can see our a is 1, our b is minus 2, and our c is minus 7. So that we can, are the solution rational? Are they real? And that I want us to think about and probably put it down in the chat. The solution to this question is it rational or real? For question 1, and look at question 2 as well. Question 2 is x squared plus x plus 1. So we already know for question 2, a is 1, b is 1, and c is also 1. So what would be the answer? Are the solutions rational? And are they real? So I'm waiting for comments on the chat before we proceed. Maybe we want to take it one by one. Okay, somebody said, and Lady Siwe said no. Okay, yeah, that was the comments for previous slide, not for this one. So I want to assume we are still busy with it. Okay, so probably we should do it together, can we? Does anybody want to say something about it? Okay, thank you, Tony. So we have x equals half, which is that divided by 2a, which is 1 over 2, 2 plus or minus root 32. And that gives 1 plus or minus 2 root 2, which are irrational and real. And for question 2, our x is equals -1 plus or minus root -3 divided by 2, which are not real because root -3 is not real. So we have seen a possible solution or possible options that answer that we are likely going to have. So the question is, yeah, let's go to the next one, Tony. Thank you.
So what we have seen is one-dimensional real numbers. Tejamade talked about the points on the line. And now we're going to introduce the idea of two-dimensional complex numbers. So when learners solve quadratic equations, they shouldn't say there are no solutions if what comes under the root sign is negative. They should say, well, we haven't learnt about them, but there's a different sort of number that we haven't met yet, and they are complex numbers. And so we're going to yet again extend our horizons, our knowledge of numbers. So real numbers are good enough for many mathematical purposes and are used in industry, commerce, science, and engineering. That's just the real numbers. But as we've seen with quadratic equations, they're not good enough for all purposes. So we need two-dimensional numbers, the complex numbers that are different, not just on a line, they won't fit on the line. That's the real numbers. Complex numbers are two-dimensional. And with complex numbers, you can solve all quadratic equations.
So we've talked about real numbers, they correspond to points on a line. Complex numbers correspond to points on a plane. They are two-dimensional. So it's written as x plus yi, which corresponds to the point on a plane with coordinates x and y. So let's find out more about the mysterious I, which we call an imaginary number, and which corresponds to the point 0, 1. So I is the square root of -1, and it's important because we can use it to solve equations.
Okay, so from the previous slide,
You're muted, Tejamade.
So I'll just carry on.
okay, yeah.
Oh, you come back, good.
Yeah, thank you. Now, so from the previous slide, we saw that I equals root -1. So now just using the algebra, work out the following examples. So we have 7 plus 6i, which is that in brackets plus brackets open, 2 plus 4i. How do we solve that? Just using the normal algebra equation that our understanding of algebra. So we have 7, we can easily do 7 and 2 and 6i and 4i. At the same time, you can also do question 2 and also 3. Okay, let's look at first and the second. How do we solve this? Very easily, we have 7 plus 2, which gives 9, and 6i plus 4i gives 10i. That is straightforward. Now let's look at the second one. 9 minus 2, that gives us 7. 10i minus 4i, that is 6i. Now, but in the case of multiplication, you want to multiply 7 plus 6i with 2 plus 4i. So that gives us 14 plus 24i squared. That is 24i squared. We get that from 6i times 4i. That gives 24i squared plus 28i plus 12i. And easily, also remember that I equals root -1. So if I equals root -1, so it means I squared equals -1. So you substitute -1 for I squared. So that gives 14 minus 24 plus 40i, and that gives us -10 plus 40i. All right, so the hint is use this multiplication to find the next answer. We want to divide. So look at what we are dividing. Minus 10 plus 40i divided by 2 plus 4i. We can immediately refer back to the example we just did now. The outcome, the final answer we got, which is minus 10 plus 40i, we want to divide it by 2 plus 4i that we used to multiply 7 plus 6i. So that tells us it's definitely going to give us 7 plus 6i, but you know the rules. We already know the rules for plus, which is addition, subtraction, multiplication, division for real numbers. The same rule holds for addition, subtraction, multiplication, and division of complex numbers. So x plus yi, where I squared equals minus 1. In mathematical language, the rational numbers, the real numbers, and complex number are three fields of numbers with the same rules. So the same rule guides all of them.
So every real number corresponds to a point on the real line, which Tejamani talked about. Every complex number corresponds to a point in the plane. So x plus I, y, the complex number, is represented by the point with coordinates x, y. So the real numbers 5 and minus 5 that you see there are on the x-axis in the diagram. The y part of that, or the imaginary part, or the complex part, is 0. 0, 5 and 0 minus 5 are 5i and minus 5i, and that's on the what you see as the y-axis. And then the 3 plus 2i is the other point that's shown in that diagram.
In 1799, so over 200 years ago, Gauss proved the fundamental theorem of algebra that every polynomial equation has a set of complex solutions that's the same number of solutions as the highest power in the polynomial. Now, bear in mind that the solutions could be repeated if the graph of the polynomial touches the x-axis, so it gives a repeated solution at that point. That means that with complex numbers, every quadratic equation has 2 solutions, every cubic equation has 3 solutions, and so on. So, for example, x squared minus y x cubed plus x squared, the one that you see on the board, is a polynomial equation with 4 solutions because 4 is the highest power of x. Now, the final point, it's a nice little point, around the year 1800, give or take, complex numbers were finally accepted as proper numbers.
So what is just school mathematics, really? Scholars, the best mathematicians, only finally understood and the complex numbers were proper numbers and they behaved like other numbers, except they were 2-dimensional. So as we saw, for human beings around the world, the understanding of numbers has developed. And now, as we are on that spiral learning path, as children are on that path, they learn about the number systems as well.
Okay, so now we want to look at this. Looking at this image, one-dimensional real numbers can be generalized to 2-dimensional complex numbers. So what about higher dimensional numbers? We know train travel in 1 dimension on a straight track. That's how train travels. What about ship? So it travels in 2 dimensions on the sea. And then we talk of rockets in 4 dimensions. So we can see we can call real number traveling in 1 dimension, which is 1-dimensional, complex numbers 2-dimensional, and quaternion 4-dimensional.
But there's no 3-dimensional numbers, although we know very well that we can travel in 3 dimensions. And in fact, it makes a lot of sense to think of 3 dimensions. There's actually not a number system in 3 dimensions. So we've been talking about 4-dimensional numbers. Now, actually, they were discovered by this Irish mathematician, William Hamilton. And the story is he was walking along the river one Sunday afternoon with his wife, and he suddenly got very excited because he suddenly realized the penny dropped, that he finally understood the whole idea about 4-dimensional numbers, and he scratched it on the stonework of the bridge. And I think there's still that, it's still there. So complex numbers are just pairs of real numbers.
Sorry, Tony, it's not just still there. There are walks, Hamilton walks done, and especially on his birthday on October the 16th. Every year there is a Hamilton walk where you can go and actually see the scratchings on the bridge.
And people celebrate it in Ireland, don't they, Caroline?
They most certainly do. They celebrate all their magnificent people.
So what Hamilton realized was that complex numbers are just pairs of real numbers, as we've seen, and quaternions are pairs of complex numbers. And so, wow, we've now got 4-dimensional numbers, and they're really a very important tool. They're frequently used in programming computer graphics and controlling machines, because the equations of rotations and reflections in 3 dimensions are given in a very simple form by quaternions. So quaternions are 4-dimensional numbers, but they're very useful in higher mathematics and in many applications. So applied mathematics and physics deal with motions in space. So quaternions are very useful there, for example, in Einstein's space-time equations. But the curious thing is there are no 3-dimensional numbers, and in fact, there are something that is sort of behave more or less like numbers in 8 dimensions, which is another power of 2, and so it goes on, but we're going to stop there.
So this is an image that has come from space. We're talking about using quaternions now, an application for using quaternions, working out the path, working out where and when the objects that we see in space happen. This is taken by the James Webb Telescope, and it has taken a picture. This was launched at the end of 2021, and it went into operation in July 2022. So it transmitted its first image in July 2022. And what you're seeing there is an image, a red smudge. It's 35 billion light years away. This is something you can use with your big numbers with your learners as well. And we see it as it was. This is what it looked like 235 million years after the Big Bang. So space and time, quaternions come into play to be able to interpret it all. Now, the James Webb Telescope was launched in December 21. It's cost $10 billion. And there's a lot of space research as well going on in South Africa with telescopes and things. I'm not sure what other countries in Africa. It's in search, we're looking beyond anything we've ever seen. It's in orbit around the sun, and it's literally in search for the beginning of time, the edge of darkness and the beginning of time. It's an infrared observatory. It's orbiting the sun. It's about 1 million miles from Earth, and it's got protection to not get burned up by the sun. And it's there to find the first galaxies that formed in the early universe and to see stars forming in planetary systems.
And this is fascinating. We're going to say a little bit more about it, but actually 235 million years is not very long in this great scheme of things, in talking about time from the beginning of time, about 235 million years. I mean, it's a long time, but it isn't, compared to 35 billion, 235 million. That's quite close to the Big Bang. So we're going a long way back now. The James Webb Telescope can go and take pictures of objects further away from us in light years, and going back towards the Big Bang, the beginning of our existence, beginning of the existence of the universe. So here we've got a picture of this James Webb Telescope. It's not the actual one, it's a replica, but it's a full-scale replica. And the picture was taken with all the people who'd worked on it standing there in front of it. So you can see you've got a sense of proportion. It's not really very big. And I've got some of these pictures from the NASA web pages, and from webtelescope.org, which is showing, there's a big gallery of images there, like the one Caroline just talked about, so you might like to have a look at that. But actually, going back to what Caroline was saying about those images and South Africa, yes, South Africa's got a lot of telescopes. You've got the Square Kilometre Array, which is a world-leading array of new telescopes. And Caroline made a comment about the rest of Africa. The interesting thing is there are astronomers now analysing these pictures right across the world, because with computers and the internet, they can receive the information from wherever the telescope is collecting the information, just as they receive the information from the James Webb Telescope, which is out there, you know, orbiting the sun. They can receive it from other telescopes, like the ones in South Africa, the Square Kilometre Array, and they can talk to each other on the internet. So they don't actually have to be physically on the site of the telescope. They can be anywhere, and they can all work together, collaborate online. Now here, this picture shows how the sun shield works. So you see in the picture above it how there are several layers there, and in this diagram you see that as the sunlight hits the outer layer, in the gap between the outer layer and the next one in, the heat sort of bounces backwards and forwards, and quite a lot of it passes out again and into the atmosphere, and then the heat that goes through the next layer of the sun shield is again bouncing around, and some of it is being emitted, and some of it is going through to the next layer, and it's getting a little bit cooler each time. And so in the fourth layer, it's even cooler, and by the time it goes through the fourth layer into where the actual telescope is, it's very little heat's getting through, and so it's the telescope isn't damaged. Well, the pictures here show you how the telescope was actually had to be folded up to fit back into the rocket. And the last picture on the right shows you an enlargement of the picture on the left. And so you're looking into the top part of the rocket there, where the telescope itself is stored, and the shields must have been, I think, whether there was, I can't quite see where they are. They were stored lower down or behind. We get slightly concealed in this picture.
I think they might be curved underneath it, behind it, but yeah, we're just guessing really. I don't think it shows as well.
Yes, that's right. Now here you see it, a diagram of it. So it's see its various parts. You can see the heat shield again. You can see that the primary mirror there, which is yellow, consists of a lot of hexagonal mirrors, and they are all capable of moving independently. and they have to be adjusted so you get a perfectly perfect surface of the mirror there, which focuses the light on the secondary mirror, which you see on the right. It's labeled. So the primary mirror focuses the light on the secondary mirror, and then the instrumentation sends the pictures back to the Earth. So the telescope had to be unfolded and it had to be adjusted so that the sun shield will protect the instruments from the sun's rays. And the number knowledge we have thought about today was used to calculate the exact angles to control the telescope and distances that ranged from less than 1/100th of a millimeter to 35 billion light years. So the knowledge of the numbers that we've been talking about is being applied here.
And on going the other way, the engineers who actually designed this, think about all the design they had to make. They had to literally not just design it, but design it to pack into the spacecraft and deploy, not only deploy, but be secure. So all those little levers you see, all those struts you see, they're all have to be stable, so stable that they can capture these tiny insignificant points of light, not insignificant, but teeny weeny points of light. And they use the same. They use the numbers on a different level. They are using using integration, differentiation. They're using, but all the numbers again are just used in real life, very much so, in order to design that. Imagine if the learners you're working with end up being an engineer designing something like that.
So this is a brand new telescope, as we said. The telescope that it's replacing is the Hubble telescope, which has served us really well, and we've got lots of wonderful information from the Hubble telescope. But this is order of magnitudes more information that we're getting now, and we will be getting in it for many years to come. Oh, wanted to just say, well, I did say that the primary mirror is made up of these hexagons, and each mirror is individually adjusted for the picture to be in focus.
You said that, Tony.
Yeah, and the point is that getting these angles right in the adjustment uses quaternions.
Yeah.
Right, we've come to a summary. Now, this is a very, very busy slide. There's a lot on the slide. And I've tried to summarize what we've been doing today. So everything we've done is somewhere on that slide. And I just want to emphasize one thing, but I'd love you to make a comment on the chat. So please make a comment on the chat. How have you found this? What does it seem like to you? Now, while you're doing that, I just want to say one thing, and that is that what we've been talking about is just the process of learning school mathematics in an informal way, in the sense that you don't use all the big words in primary school, and then making it gradually more formal when you introduce the real words that see there: commutativity, associativity, distributive law, and so on in year 9. And then thinking of the rules. And then once you put the rules into lists of, well, we had them listed as first the second list, and then the distributive law, the third rule, you have got what we then use a little bit more mathematics, not really any more complicated ideas, just new names like groups and fields. So what we have been doing is paralleling all these developments. So have you got a comment, Caroline?
The thing that I really loved, I mean, apart from the Venn diagram really summarizing all the numbers and putting them in context with each other, apart from that knowing that there's only the 2 to the index powers are the way that the numbers increase, like quaternions are 2 squared and things. Inverses, I see that really powerful, and the associativity and commutativity, really getting solid on that, whatever you, as you say, whatever you call it, getting solid on the inverses I see as really powerful in clarifying a lot of the misconceptions that exist in the learners' heads. And I'd love to hear from Matt, if Matt has something he'd like to say as well.
I'll just say I enjoyed it and found the part on rational numbers very interesting.
Is it Le
And also
Bouchon?
quaternions.
Sorry, we can't hear you, Matt. Sorry, 1 second. Okay, go ahead.
Oh, yeah, I found the part on rational numbers interesting, and also the quaternions and Hamilton. I hadn't heard about that before. So if I'm ever in Ireland, I'll go and take a look. And yeah, some really useful things for teaching the kids as well.
So everybody, please, we'd love to have some responses from you, some comments.
Melanie, who is primary level, has been working in primary level. I got lost with the imaginary number, but she's not a teacher and she's never been worked in secondary anyway. Apart from getting lost with Melanie, what else did you find anything useful? And anybody else as well? What about Tejumade?
Yeah, yes, I was going to comment as well. Now, what keeps popping up as we were just presenting and talking and chatting is that the fact that the knowledge you have now, maybe there's a particular question that looks like you are not able to solve, does not mean it doesn't have a solution. And as teachers as well, so instead of telling the learners that you don't do this, let them know that, oh no, yes, this is at your level, this is how far we have gone. As you go up, then you'll be able to advance into other areas of it. So don't let it make them feel like, yes, there's no solution to something, that they will still come up to see it. Maybe next time is going to be discussed. Or when you are in grade 5 or grade 7, that is going to be explained to you. Yeah. So that is one thing that keeps popping up. And I feel like as teachers, we should take home as well that we don't just cage the learners and say, no, we don't do that, without even letting them know why we are doing certain things. And also, not just giving them the formula. If it's possible to give them the reason behind, let them just be able to relate with whatever it is that we are passing across. Like now that we talked about, I know Caroline talked about don't subtract. Why don't you add negative number to both sides? And then you see how it is. And that gives you another understanding of another concept and say, oh, okay. So it allows them to be able to advance their mathematical grammar and all what have you. Yeah. So that is what I would like to add to this. Thank you.
Well, we're getting some comments on the chat now. Please, we'd love to have some more comments on the chat. Yeah, and I think these are really, maybe the words are off-putting, you know, but the actual rules themselves are simple. And so I think the problem is knowing what the words mean. And in fact, it's of first importance that children understand the ideas. We want them to learn the words, but we really must concentrate on the actual rules, the actual ideas themselves, and gradually introduce the words. But don't be frightened of those lists of rules, because they just summarize school mathematics. Jacob says very informative. He says he's going to rewatch bits of it. Melanie says she loved learning about the history of numbers and recognizing that there are different types of numbers that learners experience at different stages. That's the main thing, different stages, but those stages parallel the development of human knowledge over hundreds, thousands of years.
Which is a comment that Melanie made earlier, that the discovery of numbers the discovery of the numbers we know today came as a result of, because that we didn't read that one out, came as a result of not having a solution, not being able to do something. So somebody came up with the idea, okay, so we've got 0. Oh, what about negative numbers? And these all came out of a problem that existed, and then the solution was finding these new rules, which is basically discovering how mathematics works.
And we've got from Nelasiwe, I like the way you differentiate rational numbers and irrational numbers. The fact all natural numbers make a pattern or decimal digits when dividing each other. They're the rational numbers. Okay, well, we haven't got any more time, so we have to move on now.
And you're very welcome, Noko. Yeah. Yes. Thank you, Tony. So we've basically given you a picture of the development of the numbers over the last 5,000 years, and it's not from the time of Pythagoras, it's way before that. And without getting too technical, hopefully, you've got the big picture ranging from kindergarten counting numbers to the fringe of research, quaternions. We didn't go into the detail of quaternions, I couldn't have. And so, yeah, your questions and comments have already come through. So that's fantastic. We've had loads of interaction today. Thank you so much for being so enthusiastic. Tej.
Right. So we have our YouTube channel where you be able to have videos. You can just go there. I know, it's freely available. So you can just go. We have MSEC GTEN YouTube channel. You can just go there to access, and if you type on YouTube, you type math toys, so you'll be able to have access to. And we also have our Facebook page. Yes, follow us on Facebook, like us on YouTube as well. On Mondays, 5 to 6 p.m. UK time, which would be, what would that be in South Africa?
7 till 8 South Africa time.
Yeah. Okay. So, yeah. So 7 to 8 South African time. Yeah. Yeah. So that we have Happy Maths Hour every week. We would like to have you connect with us so that you can learn a lot of things. Yeah.
Jacob will be sharing the recording on the WhatsApp group, and
somebody's been scribbling. Perhaps you can remove that, Caroline.
Tony. Yeah.
And here you've got quite a lot of links. Now, what I'm going to do is to circulate this to you, this as a PDF. So you'll have all these slides, and you'll be able to look at them. And we will be putting the recording up as well. And it is going to be very useful for the people who are going to be doing our courses that start next week and the week after. So there are lots of